Deep in the cosmos, where stars gather by the millions and galaxies collide in silent chaos, there's a place where reality itself seems to bend, the Hercules Cluster. Picture this, a sprawling city of galaxies over 2 billion light-years across, packed so tightly that some of them are practically neighbors, their gravitational dances warping space and time. Yet within this cosmic metropolis, something far stranger lurks. Unexplained flashes of light flicker where no star should shine. Mysterious radio signals pulse with no discernible source. And then there are the shadows vast, inky voids where the cluster's glow simply vanishes. How can a place so full of light also harbor such profound darkness? The Hercules Cluster isn't just another dot in the sky. It's a riddle wrapped in enigma floating in the void. For centuries, we've mapped the heavens believing we understood the rules. But the Hercules Cluster laughs at our assumptions. Here, the laws of physics seem to twist, revealing phenomena that defy explanation. Take, for instance, the case of the vanishing galaxy, an entire spiral system that appeared in early telescope surveys, only to disappear without a trace decades later. No explosion, no collision, just gone. Or the eerie Hercules hums, ultra-low frequency vibrations detected by radio telescopes, humming like a cosmic tuning fork with no discernible origin. These aren't just oddities, they're cosmic breadcrumbs hinting at forces and dimensions we've yet to comprehend. And every time we think we've cracked one mystery, the cluster throws another at us as if daring us to look deeper. That's exactly what we're about to do. Buckle up, because today we're diving headfirst into the 25 most bizarre, mind-bending phenomena hidden within the Hercules Cluster. From rogue black holes racing through galaxies like invisible predators to ghostly plasma structures that defy all known models of cosmic formation, this journey will challenge everything you thought you knew about the universe. And here's the wildest part. Each of these mysteries isn't just a cosmic curiosity, they're clues, pieces of a puzzle that could rewrite our understanding of dark matter, the fabric of space-time, and even the very nature of reality itself. So if you're ready to stare into the abyss and see what stares back, let's begin. The Hercules Cluster is waiting, and its secrets are more astonishing than you can imagine. Let's start with the first and perhaps most unsettling mystery, the Hercules Cluster's missing dark matter. You'd expect a structure this massive to be teeming with it, given how dark matter acts as the invisible scaffolding of the universe, holding galaxies together with its gravitational glue. But in certain pockets of the cluster, something's off. When astronomers measured the motion of galaxies there, they found them moving too fast for the visible matter alone to explain, yet not fast enough to match the expected pull of dark matter. It's as if entire sections of the cluster are playing by different rules, leaving scientists scratching their heads. One leading theory suggests that dark matter might have been stripped away by gravitational tugs of war between galaxies, like cosmic thieves stealing the very fabric of space. Others propose we're seeing the aftermath of colossal collisions, where dark matter was flung outward like splatter from a hit and run. But here's the twist: some regions show no signs of such violence. The dark matter isn't just displaced, it's gone, with no trace of where it went or why. This isn't just a gap in our knowledge, it's a direct challenge to the foundations of modern astrophysics. If dark matter can vanish without a cosmic crime scene, what else have we gotten wrong? The implications are staggering. Our entire model of galactic evolution relies on dark matter's presence to explain how structures form. Without it, galaxies shouldn't spin the way they do, clusters shouldn't hold together, and the universe's large-scale architecture shouldn't exist as we see it. Yet, in the Hercules Cluster, reality seems to disagree. Could there be an unknown force at work, something beyond our current theories? Or is dark matter itself far weirder than we imagined, with properties that allow it to disappear under certain conditions? Every telescope trained on this anomaly brings back more questions than answers, turning what should be a cosmic footnote into one of astronomy's most urgent puzzles. If the missing dark matter feels like a cosmic magic trick, then the next phenomenon cranks the weirdness up even higher, a radio signal that shouldn't exist. Deep within the Hercules Cluster, astronomers have detected a bizarre transmission that pulses with eerie regularity, yet defies every attempt to pinpoint its origin. Dubbed the phantom repeater, this signal doesn't behave like anything we've seen before. Most cosmic radio bursts are one-off blips, explosions, or collisions shouting into the void. But this one keeps coming back like a clockwork whisper from the abyss, and its pattern is anything but predictable. Sometimes it fades for months, even years, only to return with unnerving precision. Other times it stutters, flickering on and off like a dying flashlight. What makes the phantom repeater so baffling isn't just its persistence, it's the fact that every time scientists trace its path, they hit a wall. There's no pulsar spinning wildly at the source, no colliding neutron stars, not even a hint of a black hole's gravitational fireworks. It's as if the signal materializes out of thin space, broadcasting from nowhere. One theory suggests it could be a previously unknown type of magnetar, a highly magnetic neutron star with behavior so extreme it bends our understanding of physics. But magnetars usually leave traces: X-rays, gamma rays, some kind of cosmic fingerprint. This signal is ghostly clean, offering no secondary clues to its identity. Then there's the timing. Unlike human-made signals which follow strict schedules or natural cosmic events which obey physical laws, the phantom repeater seems almost capricious. It's not random, but it doesn't follow a discernible rhythm either. Some researchers have compared it to a malfunctioning beacon, as if some ancient, broken machine is sporadically powering up, broadcasting its cryptic message before shutting down again. Of course, that's pure speculation, but when mainstream science comes up empty, even the wildest ideas start to feel worth considering. The real shocker. This isn't the only signal of its kind. Similar repeating bursts have been detected in other parts of the universe, though none with quite the same irregular cadence as the Hercules Cluster's phantom. That raises an even bigger question. Are these signals natural phenomena pushing the limits of known physics, or could they be something else entirely? The possibility of artificial origins, whether from advanced civilizations or as yet undiscovered cosmic phenomena, lingers at the edges of scientific debate, not as a conclusion but as a reminder of how much we still don't understand. For now, the phantom repeater remains one of the Hercules Cluster's most tantalizing enigmas. Every time it activates, telescopes scramble to capture more data, hoping for a breakthrough. But so far, the signal keeps its secrets, pulsing silently across the cosmos, a riddle wrapped in static. And with each failed attempt to decode it, one thing becomes clearer. Somewhere in that distant cluster, the universe is playing a game, and we're still learning the rules. Amid the swirling chaos of the Hercules Cluster, where galaxies jostle for dominance like ships in a cosmic storm, there's one that seems to dance to its own rhythm, a renegade galaxy moving in ways that defy gravity itself. Nicknamed the floating galaxy, this spiral anomaly drifts against the cluster's gravitational current, as if some unseen hand is guiding it. Normally, galaxies in dense clusters follow predictable paths tugged by the collective pull of their neighbors. But this one, it's practically moonwalking through space, gliding in a direction that makes astrophysicists double-check their calculations. At first glance, the floating galaxy shouldn't exist, or at least it shouldn't behave this way. When researchers mapped its trajectory, they found it moving nearly perpendicular to the expected flow, like a salmon swimming upstream in a river of stars. The immediate assumption was a measurement error, but repeated observations confirmed the impossible. This galaxy isn't just resisting gravity, it's ignoring it. So what could explain such a defiance of cosmic norms? One possibility is dark matter again. But this time, it's not about absence, it's about distribution. Some theorists suggest the floating galaxy might be surfing a hidden wave of dark matter, a dense filament or cosmic highway that redirects its motion. Imagine a surfer catching a current unseen from shore, carried along by forces invisible to the naked eye. If dark matter isn't evenly spread but clumped in tendrils, this galaxy could be riding one, escaping the cluster's gravitational grip. Then there's the more unsettling idea. We might be witnessing a primordial flaw in our understanding of gravity itself. Newton's laws and Einstein's relativity have held up for centuries, but what if, under extreme conditions like those in the Hercules Cluster, gravity doesn't work quite the way we think? Modified Newtonian dynamics, or MND, proposes tweaks to gravitational equations to explain oddities like this without invoking dark matter. Yet even MND struggles to account for the floating galaxy's specific defiance, leaving scientists to wonder if an entirely new force is at play. Of course, there's a simpler explanation, one that's almost as jarring. What if the galaxy isn't floating at all but being pushed? Simulations show that galactic collisions can slingshot survivors at bizarre angles, like a pinball ricocheting off bumpers. If this galaxy endured a near miss with a massive neighbor, the gravitational kick could have sent it careening off course. But here's the catch: no such collision scars or nearby culprits have been found. The floating galaxy appears pristine, its spiral arms undisturbed, as if it decided to break the rules all on its own. The deeper astronomers dig, the more perplexing it becomes. Recent studies even suggest the galaxy's motion might be tied to the cluster's larger-scale flows, vast rivers of gas and dark matter that weave through Hercules like cosmic conveyor belts. If true, the floating galaxy isn't a rebel, it's a passenger caught in a current we're only beginning to map. But until we can see these hidden structures directly, the mystery remains wide open. What makes this phenomenon so thrilling isn't just the defiance of expectations, it's the reminder that the universe still holds cards we haven't even glimpsed. Whether it's unseen matter, uncharted forces, or gaps in our foundational theories, the floating galaxy challenges us to question not just what we know, but how we know it. And in that challenge lies the spark of discovery, the chance to rewrite the cosmic rulebook, one defiant galaxy at a time. Deep within the swirling expanse of the Hercules Cluster, there's a boundary that shouldn't exist, a cosmic wall where high-energy particles simply vanish. Imagine hurling a handful of sand into the wind, only to watch it stop midair as if hitting an invisible shield. That's precisely what happens here. Cosmic rays, those ultra-fast particles racing across the universe, slam into some unseen force and disappear. No gradual fade, no deflection, just an abrupt stop, like a car hitting an unseen barrier at full speed. This isn't just a curiosity, it's a cosmic crime scene with no obvious culprit. So what could create such an invisible boundary? One leading suspect is magnetism. The Hercules Cluster is laced with powerful magnetic fields, woven through its galaxies like an invisible spiderweb. These fields might be strong enough to deflect or even trap incoming particles, acting like a cosmic filter. But here's the problem: the fields we've detected shouldn't be this powerful. They're like a gentle breeze trying to stop a bullet, yet somehow they're succeeding. Some researchers suggest the cluster's magnetic web might be tangled in ways we don't yet understand, amplifying its strength in localized knots. Others propose these fields are supercharged by the cluster's extreme environment, where galaxies collide and gases swirl at temperatures in the millions of degrees. Then there's the wilder possibility: dark matter again. Could this barrier be a dense concentration of dark matter, so massive it warps space-time enough to halt particles in their tracks? It's a stretch, but not impossible. Dark matter's gravitational pull might create a sort of cosmic dam, redirecting or absorbing anything that gets too close. Yet even this theory falters when confronted with the barrier's razor-sharp edge. Gravity usually creates gradients, not hard stops. So why does this boundary look more like a door slammed shut than a hill gradually climbed? The most tantalizing and unsettling hypothesis is that we're seeing evidence of physics beyond the standard model. Some theorists whisper about exotic fields, hypothetical forces or particles that could interact with cosmic rays in ways we've never observed. Picture an invisible fence made not of matter or energy, but of something entirely new, a property of the universe we've yet to name. If true, this barrier isn't just a curiosity. It's a portal to a deeper layer of reality, one where the rules we take for granted no longer apply. What makes this phenomenon so pivotal isn't just its mystery, it's the way it forces us to question the tools we use to explore the cosmos. Our telescopes and detectors are built to find what we expect to find. But the Hercules Cluster's invisible barrier whispers a humbling truth. The universe might be playing by rules we haven't even imagined yet. Every time we try to pin it down, it slips through our fingers, leaving us with more questions than answers, and proving once again that the cosmos loves a good plot twist. Now picture two cosmic monsters lurking in the heart of the Hercules Cluster, twin supermassive black holes, each weighing billions of times the mass of our Sun, separated by just a few thousand light-years. They should be nearly identical, born from the same violent mergers that shaped their corner of the universe. Yet one devours matter with reckless abandon, spewing jets of radiation visible across the cosmos, while the other sits in eerie silence, a dark giant refusing to feed. This isn't just a curiosity, it's a full-blown cosmic paradox challenging everything we thought we knew about how black holes grow and evolve. Take the active one first, a ravenous beast astronomers call Hercules X1. It's a crescent disk, the swirling ring of doomed matter spiraling toward oblivion, burns so bright it outshines entire galaxies. Jets of plasma shoot from its poles at near light speed, carving bubbles in the surrounding gas that glow for millions of light years. This is a black hole in its prime, a gravitational predator at the peak of its power. But just a cosmic stone's throw away, its twin, Hercules X2, is the opposite, a dormant titan. No jets, no glowing disk, just an unfathomable mass lurking in the dark, its presence betrayed only by the way nearby stars whip around. Nothing. Why such extreme differences? The leading theory points to their feeding habits. Active black holes usually sit in gas-rich environments, gorging on stellar debris or interstellar clouds. But the quiet twin should have the same menu. Both galaxies here are similarly massive, similarly positioned in the cluster's dense core. Yet one feasts while the other fasts, as if invisible bouncers are letting matter into one club while turning it away from the other. Some researchers suggest magnetic fields might be the gatekeepers, funneling material toward one black hole while starving its neighbor. Others propose that past collisions left X2's surroundings too turbulent for stable feeding, like trying to drink from a fire hose. Then there's the timing angle. Black holes aren't always active. They cycle between feast and famine over millions of years. Could we just be catching X2 during a cosmic nap? Possibly, but the odds of seeing twins in such starkly opposite phases simultaneously are astronomically low. That's led to bolder ideas, like one black hole stealing the other's lunch. Simulations show that in dense clusters, black holes can shadow each other, their gravitational wakes diverting gas flows unpredictably. Imagine two whirlpools side by side, one hogging the current while the other sits eerily still. But the real shocker, the quiet twin might not be quiet at all. Recent observations hint that X2 could be emitting faint, ultra-low frequency gravitational waves, ripples in space-time too subtle for our current detectors to confirm. If true, this black hole isn't dormant, it's dining in stealth mode, swallowing matter so efficiently that almost no light escapes. That would rewrite the playbook on black hole activity, suggesting some monsters prefer their meals without the cosmic fireworks. Whatever the explanation, these mismatched twins force us to rethink black hole ecology. Are they products of their environment, or does randomness play a bigger role than we thought? Could their differences hint at entirely separate evolutionary paths, like siblings raised in the same house but destined for opposite fates? Every telescope trained on this duo brings back more puzzles than answers, proving even the darkest giants in the universe still have secrets to surrender. Nestled in the bustling heart of the Hercules Cluster, there's a star so old and chemically bizarre that it shouldn't exist at all. Meet Hercules Prime, a celestial relic that's been burning for over 13 billion years, nearly as ancient as the universe itself. At first glance, it looks like any other aging star, its light dimmed by eons of nuclear fusion. But when astronomers analyzed its composition, they hit a cosmic roadblock. This star is packed with elements like gold, platinum, and uranium, in quantities that defy every model of stellar evolution. According to our understanding, stars this old should be made almost entirely of hydrogen and helium, the primordial ingredients of the early cosmos. Yet Hercules Prime is practically a periodic table on fire, flaunting heavy metals like a cosmic alchemist's masterpiece. So how did this ancient anomaly get so blinged out? The answer could rewrite the entire timeline of star formation. Normally, heavy elements are forged in two ways: the nuclear furnaces of massive stars or the cataclysmic explosions of supernova. But here's the catch: both processes take time. Generations of stars must live, die, and scatter their enriched ashes into space before new stars can incorporate those materials. Hercules Prime, though, is too old to have had that chance. It was born when the universe was just a toddler, before enough stellar deaths had occurred to seed space with heavy elements. It's like finding a medieval knight with an iPhone. The timeline just doesn't add up. One theory suggests this star might be a cosmic cannibal, having devoured smaller, metal-rich neighbors over its lifetime. Picture a stellar Pac-Man growing heavier with each galactic bite, but even that doesn't fully explain its composition. The ratios of certain elements, like the eerie abundance of europium, don't match the debris of typical stellar collisions. Another idea pushes the boundaries even further. What if Hercules Prime formed directly from the remnants of an entirely different kind of star, one that existed briefly in the early universe and has since vanished? Hypothetical population Roman 3 stars, the universe's first generation, are thought to have been monstrously massive and short-lived, dying in explosions far more violent than modern supernova. If one of these primordial giants seeded Hercules Prime, it could account for the star's impossible chemistry, but the most radical possibility: we might be looking at the ashes of a neutron star collision. These ultra-dense corpses, when they slam together, are known to forge gold and other heavy elements in staggering amounts. If a neutron-star merger happened unusually early in cosmic history, perhaps in the same pocket of space where Hercules Prime was forming, it could have sprayed the young star with a treasure trove of metals. That would mean such collisions occurred billions of years earlier than we thought, forcing us to redraw the cosmic calendar of element creation. The implications are staggering. If stars like Hercules Prime exist, the early universe might have been far more chaotic and productive than we ever imagined. Entire chapters of stellar evolution could be missing from our textbooks. Even the origins of life's building blocks, carbon, oxygen, iron, might need revisiting, as these elements could have been sprinkled into the cosmos much sooner than current theories allow. Hercules Prime isn't just a stellar oddity. It's a time capsule offering a glimpse into an era when the rules of the universe were still being written. And with every new observation, it whispers the same tantalizing question: what else have we gotten wrong about the dawn of time? Among the bustling giants of the Hercules Cluster, the smallest members are vanishing without a trace. Dozens of dwarf galaxies, each once a faint but stable part of the cosmic neighborhood, have simply blinked out of existence. These aren't galaxies torn apart by collisions or faded into obscurity over eons. They're here one moment, visible in telescope surveys, and gone the next, as if someone flipped a switch. For astronomers, it's like watching a forest lose its underbrush overnight with no storm or fire to explain the disappearance. The leading theory points to dark matter, yet again, but with a sinister twist. Dwarf galaxies are thought to be anchored by dense halos of this invisible substance, which keeps their stars bound together despite their modest size. But simulations suggest that in the Hercules Cluster's extreme gravitational environment, dark matter halos might be getting stripped away, like thieves in the night stealing the very glue that holds these galaxies together. Without that scaffolding, stars would scatter, leaving no visible wreckage behind. It's a cosmic vanishing act where the magician's trick is gravity itself. There's another, more unsettling possibility. What if these galaxies aren't vanishing naturally at all? Some researchers have floated the idea, albeit cautiously, that advanced civilizations could be the culprits. On a long enough timeline, a sufficiently advanced society might harness the energy of entire galaxies, dismantling them for resources or even altering their structure to avoid detection. It's a Fermi paradox staple, the notion that silence in the universe might not mean absence but obscurity. If a civilization reached Type 3 on the Kardashev scale, capable of manipulating galaxies, their signature might look eerily like these sudden disappearances. No explosions, no debris, just silence where there once was light. Of course, the scientific community leans heavily toward natural explanations. One compelling alternative suggests these dwarfs might be victims of tidal disruption, stretched to invisibility by the cluster's immense gravity. Imagine a handful of sand tossed into a whirlpool. The grains don't vanish, but they become too diffused to spot. Yet even this explanation has holes. Tidal disruption usually leaves behind streams of stars, faint but detectable. In Hercules, the dwarfs vanish cleanly, leaving no such trails. The mystery deepens when you consider timing. These disappearances aren't spread evenly across millions of years. They seem clustered, as if triggered by some unseen wave passing through the region. Could the cluster's dark matter be arranged in clumps or waves that occasionally reset its smaller galaxies? Or is there a hidden player, a rogue black hole, perhaps wandering the cluster like a cosmic grim reaper, erasing dwarfs from existence as it passes? The stakes here are higher than just solving a celestial whodunit. Dwarf galaxies are the building blocks of the universe, the remnants of its earliest days. If they can vanish this abruptly, our models of galactic evolution and even the fate of our own Milky Way might need serious revision. Every missing dwarf is a data point lost, a puzzle piece we can't put back. And with each one that disappears, the Hercules Cluster whispers a haunting question. In a universe full of darkness, how much are we still failing to see? Amid the densely packed galaxies of the Hercules Cluster, where celestial neighbors jostle for space like commuters in a cosmic subway, there's a gaping absence, an emptiness so vast and precise it feels intentional. Astronomers call it the Great Void, a spherical region stretching nearly 3 million light-years across, where not a single galaxy, star, or even a wisp of interstellar gas lingers. It's not just quiet, it's eerily empty, a perfect bubble of nothingness in a universe that abhors a vacuum. Cosmic voids aren't new, the universe is speckled with them like holes in Swiss cheese. But those voids form naturally, carved out by the large-scale structure of the cosmos, where matter clumps together and leaves gaps in between. The Hercules Great Void defies that logic. It's too round, too clean, and most baffling of all, it sits smack in the middle of one of the densest regions of space we've ever observed. Imagine finding a perfectly dug pit in the center of a bustling city, with no construction crew or geological event to explain it. That's the level of absurdity we're dealing with here. So what could carve out such a pristine pocket of nothing? One theory suggests a runaway collision of supermassive black holes. When two of these monsters merge, they can recoil from the gravitational waves they produce, shooting off like a rocket and clearing everything in their path. But for a void this size, the energy required would be unimaginable enough to fling not just stars, but entire galaxies out of the way. And yet, there's no trace of such a cataclysm, no swirling debris, no ghostly shocks in the surrounding gas. Just silence. Then there's the darker possibility. Could this void be evidence of something artificial? Before you dismiss that as science fiction, consider the numbers. A Type 3 civilization on the Kardashev scale, one capable of harnessing the energy of galaxies, might theoretically construct megastructures on scales we can barely comprehend. Could the Great Void be the footprint of such a project, a sphere of space deliberately emptied for reasons beyond our grasp? It's a wild idea, but in a universe this old and vast, the line between natural and unnatural blurs at the edges. Of course, the likelier explanation is still cosmic, just stranger. Some astronomers speculate that the void could be a false vacuum bubble, a relic from the universe's infancy when the very fabric of reality underwent phase transitions like water freezing into ice. If a patch of space crystallized differently from its surroundings, it might repel normal matter entirely, creating a permanent desert in the cosmos. It's a fringe idea, but fringe ideas have a habit of becoming mainstream when the universe throws us curveballs like this. The greatest puzzle isn't the void itself, it's the reaction of the galaxies around it. Instead of drifting inward to fill the emptiness, they seem to avoid it entirely, as if repelled by an invisible force. That behavior has no precedent in our models of gravity or dark matter. It's as if the void isn't just empty space, but space that actively resists being filled. Whether natural or not, the Hercules Great Void forces us to confront an uncomfortable truth. There are still forces at work in the universe we don't just fail to understand, we fail to even notice until they punch a hole in reality itself. And in that silent, perfect sphere of nothing, the cosmos might be hiding its most unsettling lesson yet. Sometimes absence isn't just absence, it's a message written in the negative space between the stars. In the Hercules Cluster, even death has a sense of timing, sometimes too perfect a sense. Astronomers have observed multiple supernovae, those catastrophic stellar explosions, detonating in near-perfect synchronization across galaxies that should have no connection. These aren't just coincidental blips, they're paired events, sometimes separated by mere hours despite occurring light years apart, as if some unseen conductor cued their final notes. The odds of this happening by chance are astronomically low, like flipping a coin 1,000 times and getting heads every single time. So what cosmic puppet master could be pulling the strings behind these synchronized deaths? One clue lies in the stars themselves. These aren't just random supernovae, they are all type Ia, the kind that occur when white dwarf stars steal too much mass from a companion and cross a critical threshold. The eerie precision of their explosions has long made them standard candles for measuring cosmic distances, but in the Hercules Cluster, that precision has gone haywire. Normally, the process takes millennia of gradual mass transfer, yet here, stars separated by vast distances seem to hit their breaking points in lockstep. Could some external trigger, a wave of dark matter, a ripple in spacetime, be nudging them toward doom simultaneously? The plot thickens when you examine the cluster's magnetic fields. Hercules is laced with some of the most intense fields ever observed, woven through its galaxies like invisible threads. Some theorists suggest these fields might transmit shocks or quantum fluctuations, acting as a cosmic domino chain that tips unstable stars over the edge in unison. It's a stretch, but not impossible. Alternatively, the cluster's dense environment might be seeding synchrony through sheer gravitational chaos. As galaxies brush past one another, their tidal forces could destabilize white dwarfs in similar ways, like a crowd jostling multiple cups to the edge of a table at once. Then there's the nebula, a sprawling cloud of gas and dust nicknamed the alchemist's crucible for its impossible chemistry. Nestled near the synchronized supernova, this structure glows with elements that shouldn't coexist: neon alongside platinum, helium tangled with uranium. Such mixtures defy our understanding of nucleosynthesis, the process by which stars forge heavier elements. Normally, these materials form under wildly different conditions: explosive, high-energy environments for some, slow cosmic simmering for others. Yet here they are, tossed together like ingredients from unrelated recipes. The most tantalizing link: the nebula's strange brew lines up almost perfectly with the synchronized supernova's fallout zones. It's as if the explosions didn't just happen together, they cooked together, their debris mingling in ways that left behind a chemical fingerprint no single supernova could produce. That raises a dizzying possibility. Could these events be part of some larger, unseen process? A supernova factory where stars are pushed to explode not just in sync, but as part of a chain reaction we've yet to map. There's a wilder angle, too. Some researchers speculate that the nebula's impossible mix might be evidence of exotic physics, particles or forces beyond the standard model, altering the rules of elemental creation. If true, the Hercules Cluster isn't just breaking the mold, it's rewriting the periodic table in real time. Whether through hidden triggers, gravitational chaos, or something even stranger, these paired phenomena remind us that the universe's greatest explosions might not be solo acts, but coordinated performances orchestrated by laws we're only beginning to hear. Time behaves strangely around black holes, we know this. The immense gravity slows its flow, creating a cosmic version of quicks, and where seconds stretch into minutes. But in the Hercules Cluster, something's off. The black holes here aren't just bending time predictably, they're warping it inconsistently, as if space-time itself has developed a glitch. Observations reveal wild variations in time dilation around otherwise similar black holes, some where clocks tick barely slower than normal, others where time nearly grinds to a halt, with no clear explanation for the disparity. It's like watching pendulums swing at different speeds in the same room, defying the laws of physics we thought were universal. Take Hercules X3, a midweight black hole with the gravitational pull you'd expect from its size. Yet stars orbiting it experience time dilation so extreme that a single hour for them equals 3 years for distant observers. Right next door, Hercules X4, a black hole with nearly identical mass, barely stretches time at all. According to Einstein, time dilation should scale neatly with mass and proximity. So why are these cosmic twins playing by different rules? One possibility cuts to the heart of modern physics. What if space-time isn't as uniform as we think? The cluster's extreme density might be stressing the fabric of reality itself, creating localized knots where gravity behaves unpredictably. Picture a rubber sheet draped over a bed of nails. Some areas sag smoothly, others crumple chaotically. If space-time in Hercules has similar wrinkles, it could explain why time stutters unevenly around its black holes. Then there's the dark matter angle again. Simulations suggest certain dark matter distributions could amplify or dampen gravitational effects unevenly, like an invisible lens warping spacetime's behavior. But here's the twist: we've never observed dark matter counteracting gravity to this degree. If that's happening, it implies dark matter interacts with spacetime in ways our models never accounted for, perhaps even exerting negative pressure, like a cosmic buffer slowing time's distortion. The boldest theory: these anomalies might be evidence of quantum gravity effects bleeding into the macroscopic world. At tiny scales, physicists suspect spacetime is foamy and turbulent, but Hercules' black holes could be magnifying that turbulence to observable levels. Imagine pouring water through two identical sieves. One lets liquid flow smoothly, the other sprays in random directions. If spacetime has a hidden graininess, black holes might reveal it by how unpredictably they stretch time. What unsettles scientists most isn't just the inconsistency, it's the patterns. Certain black holes in Hercules show cyclical shifts in their time dilation, as if an unseen dial is being tweaked periodically. No known astrophysical process explains this. No star's orbit, no jet's pulse aligns with these changes. It's as if the cluster itself is a lab where spacetime's rules are being rewritten on the fly, and we're only catching fragments of the experiment. Every telescope pointed at these black holes brings back more contradictions. Some clocks speed up briefly before slowing again, like time itself is gasping for air. Others show bizarre echoes where dilation effects ripple outward long after stellar material falls in. These aren't just quirks, they're cracks in the foundation of relativity, hinting that in the Hercules Cluster, space-time doesn't just bend, it fractures. And until we understand why, every tick of the cosmic clock comes with a question mark. Drifting through the Hercules Cluster like a cosmic outcast, there's a planet that shouldn't be here, a solitary world, untethered to any star, humming with a metallic song. This rogue planet, designated HCP-13 by astronomers, emits radio pulses so precise they resemble the ticking of a celestial clock, yet their frequencies match no known natural source. Even more baffling, its composition. Scans reveal a surface crust laced with pure iron alloys, a core denser than any planetary model predicts, and a magnetic field strong enough to deflect solar winds from light years away. This isn't just a wanderer, it's a relic of something far stranger, a puzzle wrapped in layers of impossible physics. How does a planet like this even form? Conventional wisdom says planets coalesce from the dusty disks around young stars, their cores building up gradually over millions of years. But HCP-13's core is a monstrosity, a solid sphere of crystallized metals, some of which shouldn't exist in such purity outside a supernova's forge. One theory suggests it might be the shattered heart of a failed star, a brown dwarf that somehow had its outer layers ripped away, leaving behind this metallic husk. Another proposes it's the remnant of a colossal collision between two protoplanets, their cores fusing in a cataclysm so violent it birthed this abomination of density. Then there's the sound. The radio emissions pulsating from HCP-13 aren't random. They oscillate in mathematically perfect intervals, like a sinusoidal wave composed by a cosmic mathematician. Natural processes rarely produce such purity. Neutron stars come closest with their precise pulses, but even their signals scatter slightly over time. This planet's frequencies, though flawless. That's led to wilder speculation. Could its core be some kind of natural quantum oscillator, a crystalline structure vibrating at frequencies dictated by atomic lattice vibrations? Or more controversially, are we hearing the echoes of an ancient artificial engine buried deep within, still running on autopilot long after its builders vanished? The planet's journey only deepens the mystery. Rogue planets aren't unheard of, but they're usually ice-covered nomads flung from their star systems by gravitational chaos. HCP-13, though, moves with eerie purpose. Its trajectory suggests it didn't just wander into the Hercules Cluster, it accelerated here as if drawn by some unseen force. Simulations show it couldn't have reached its current speed through gravity alone. Something gave it a kick, a nudge that defies the cluster's natural dynamics. Was it slingshot by a black hole, propelled by its own magnetic field interacting with the cluster's filaments? Or is there something embedded inside it, a relic or mechanism still active, steering this world like a ship with no captain? Whatever the truth, HCP-13 challenges our most basic assumptions about planetary science. It's a reminder that the universe doesn't just break rules, it invents new ones in the quiet corners of space, where no one's watching until the anomalies grow too loud to ignore. And as this metallic rogue drifts deeper into the Hercules Cluster, its pulses grow stronger, as if it's not just a curiosity but a beacon, waiting for something or someone to finally listen. Somewhere in the Hercules Cluster, light is playing tricks on us. Echoes from explosions that died out millennia ago are only just reaching us now, looking suspiciously fresh. These light echoes behave like cosmic mirages arriving decades, even centuries later than they should, as if time itself has gotten tangled in the cluster's dense web of galaxies. Normally, when a star explodes, its light races outward in all directions at, well, the speed of light. But in Hercules, some of that light takes the scenic route, bouncing off interstellar dust, weaving around gravitational bends, and showing up fashionably late to the party with hardly any redshift to show its age. The weirdest part, these echoes aren't just delayed, they're bright, as if the original explosion happened far more recently than our cosmic records claim. One particular echo, nicknamed Hercules Ghost, appears to originate from a supernova documented in the late 19th century, yet its light reaches us with the crisp intensity of an event that occurred mere decades ago. It's like hearing an echo shout back at you louder than your original voice. How does light not only get stuck in traffic but arrive with its energy seemingly intact? Astronomers suspect the cluster's absurdly packed environment is to blame. With galaxies crammed so closely together, their collective gravity warps space-time into a labyrinth of lenses and mirrors. Light traveling through this mess doesn't just follow a straight line, it pinballs between gravitational wells, taking detours that stretch its journey without necessarily dimming its punch. Some paths might even amplify the light through a process called gravitational lensing, where spacetime's curvature acts like a magnifying glass. Imagine a flashlight beam bouncing between a room full of mirrors. Some reflections arrive late, but a few might hit your eyes brighter than the original beam if they've been focused just right. But the real head-scratcher is the timing mismatch. Light echoes usually redshift over time, their wavelength stretching as the universe expands. Yet several Hercules echoes skip this cosmic aging process entirely, their spectral fingerprints suspiciously youthful. One theory points to the cluster's unique dark matter distribution. Perhaps certain dense pockets act like time capsules, temporarily shielding light from the universe's expansion. Another, more radical idea suggests we're seeing evidence of tired light, a once-discarded hypothesis where photons lose energy not from cosmic expansion, but from interacting with some unknown medium in space. If true, it would upend our entire understanding of how light travels across the universe. The implications ripple far beyond Hercules. If light can be delayed, amplified, or even preserved like this, our cosmic distance measurements, many of which rely on the predictability of light's behavior, might need recalibrating. Supernova we thought were 10 billion light-years away could be closer or farther, depending on what detours their light took. Even the universe's expansion rate, calculated using these celestial yardsticks, might carry hidden errors. What makes these echoes so thrilling isn't just their defiance of physics, it's their persistence. They keep showing up unprompted in telescope data, like a cosmic prankster lobbing surprises into our models. And with each new one we catch, the Hercules Cluster whispers the same unsettling question. If light itself can't be trusted to play fair, what else have we misunderstood about the fabric of reality? Stretching across the Hercules Cluster like the hum of a distant, unfathomable machine, there's a sound that shouldn't exist, a deep, rhythmic vibration thrumming at frequencies so low they border on imperceptible. Astronomers call it the Hercules Whisper, a series of ultra-low frequency waves detected by radio telescopes, pulsing through the cosmos with the consistency of a heartbeat but the origin of a ghost. These aren't the chaotic ripples of colliding galaxies or the leftover echoes of black hole mergers. They're too clean, too precise, as if the universe itself is humming a tune we've never been meant to hear. What makes the whisper so unsettling isn't just its mystery, it's the way it defies every conventional explanation. Typical cosmic vibrations come from recognizable sources, neutron stars spinning wildly, supernova shockwaves rippling through gas clouds, even the faint tremors of the universe's birth in the Big Bang. But the whisper doesn't match any of these. Its frequencies are lower than anything naturally occurring, dipping into ranges that would require something truly colossal to generate something on the scale of galaxy clusters themselves. Yet when astronomers trace the waves back to their source, they find nothing. No lurking black hole, no hidden structure, just empty space humming with energy. One theory stretches the limits of known physics. Could these waves be evidence of colliding dimensions? In certain branches of string theory, our universe isn't the only one. It's just one brain, floating in a higher dimensional space, occasionally brushing against others. If such a collision happened within or near the Hercules Cluster, the resulting vibrations might manifest as these eerie low-frequency waves. Imagine two sheets of paper fluttering in the wind, barely touching. Only in this case, the paper is space-time itself, and the touch sends shockwaves through reality. Then there's the darker, more tantalizing possibility. The whisper might be a relic of the universe's birth, a primordial remnant from the first fraction of a second after the Big Bang. In that chaotic infancy, the cosmos underwent a period of rapid expansion called inflation, which could have left behind gravitational, fossils, waves trapped in the fabric of space-time like wrinkles in a frozen lake. Hercules, as one of the most massive structures in the observable universe, might be amplifying these whispers from the dawn of time, making them audible to our instruments for the first time. But the most provocative clue lies in the whisper's structure. Unlike random cosmic noise, these waves carry faint but detectable patterns, almost like a code. Some researchers have noted recurring intervals in the pulses, subtle repetitions that hint at an underlying order. Natural phenomena rarely produce such regularity without a clear mechanism. Could this be the signature of an unknown astrophysical object? A cosmic string, a theoretical defect in space-time thinner than an atom but stretching across galaxies, might vibrate with this kind of precision. Or perhaps it's something even stranger, a shadowy form of matter or energy oscillating in ways we've yet to imagine. The implications ripple far beyond Hercules. If these waves originate from beyond our known physics, they could be the key to unlocking dark matter's secrets or even proving the existence of parallel universes. Every new detection adds another piece to the puzzle, but the full picture remains maddeningly out of reach. The Hercules whisper isn't just a sound, it's a question echoing across the cosmos, waiting for someone to finally understand the answer. There's a pair of quasars in the Hercules cluster that shouldn't be connected, yet they flicker in perfect unison, like cosmic twins separated at birth. These radiant behemoths, designated Q114 and Q117, are separated by over 50,000 light-years, far enough that no known force could synchronize their behavior. Yet their light curves match exactly, their brightness rising and falling in lockstep as if sharing an invisible script. Normally, quasars, the blazing cores of distant galaxies powered by ravenous black holes, flare and dim unpredictably, their frenetic feeding habits as erratic as a stormy sea. But these two, they're dancing, and their choreography defies every law of classical physics. The leading explanation dives into the quantum realm. Under certain conditions, particles can become entangled, their states linked instantaneously across vast distances, a phenomenon Einstein famously dismissed as spooky action at a distance. But in the Hercules cluster, that spookiness might be scaling up catastrophically. Could these quasars be entangled on a galactic level? Some theorists suggest their supermassive black holes might have once been part of a single, unfathomably dense object, a binary black hole so tightly bound that its split sent shockwaves through spacetime itself, leaving their remnants forever linked. It's as if the universe tied an invisible thread between them, one that tugs at their activity in ways we're only beginning to suspect. Yet entanglement alone doesn't explain the sheer precision of their synchronicity. Even in quantum experiments, tiny disturbances eventually break the connection. These quasars, though, have mirrored each other flawlessly for centuries of observations. That's led to wilder ideas like the cluster's extreme gravity warping causality, or hidden dimensions acting as a conduit between them, one particularly mind-bending proposal. The quasars might not be separate objects at all, but projections of a single higher dimensional structure, like shadows cast by a spinning shape appearing distinct from our limited perspective. Meanwhile, just a cosmic stone's throw away, another anomaly lurks, the Hercules cold spot. Imprinted on the cosmic microwave background, the afterglow of the Big Bang. This region is noticeably colder than its surroundings, as if someone pressed an icy finger against the fabric of the early universe. Such cold spots aren't unheard of, but Hercules' version is too cold, too large, and most suspiciously aligned eerily close to the entangled quasars. Coincidence unlikely. The cold spot's leading explanation ventures into multiverse territory. Some cosmologists suggest it might be a bruise left by a collision with another universe during inflation, a time when our cosmos ballooned exponentially in size. If a neighboring universe bumped into ours, the energy transfer could have left behind this chilly fingerprint. Alternatively, it could mark the presence of a cosmic defect, a texture, in space-time where the laws of physics briefly twisted during the universe's birth. But what if the cold spot and the quasars are connected? Here's where things get truly surreal. If the cold spot is a multiverse artifact, could the entangled quasars be its anchor points, a kind of cosmic stitching where realities briefly touched? Or perhaps the cold spot's anomalous gravity is warping space-time so severely that it's enabling quantum effects on scales we've never dreamed possible. The implications rewrite the boundaries of physics. If quantum entanglement can scale to galactic proportions, or if multiverse collisions leave detectable scars, then the Hercules Cluster isn't just a collection of oddities, it's a laboratory for realities beyond our own. Every observation tightens the knot between these phenomena, pulling us deeper into a mystery where the answers might lie not just in the stars but between them. And with each new clue, the universe whispers a tantalizing question: how much stranger can it get? The universe is expanding, that much we know, but in the Hercules Cluster, something's gone off script. While the cosmos at large grows steadily, pushed apart by dark energy's gentle nudge, Hercules is practically sprinting into the void, its galaxies hurtling away from each other at speeds that make astronomers triple-check their calculators. This isn't just a slight discrepancy, it's a full-blown cosmic mutiny, as if the cluster decided to rewrite the rules of cosmic expansion in real time. And the closer scientists look, the stranger it gets. Dark energy, the mysterious force driving the universe's acceleration, should act uniformly like an invisible tide lifting all boats. But in Hercules, the effect is uneven, almost capricious. Some galaxies race outward as if propelled by rockets, while others inch along at the expected pace. It's as if dark energy here has dials cranked to different settings in different corners of the cluster. One theory suggests the cluster might be sitting atop a dark energy hotspot, a rare concentration of this enigmatic force amplifying its effects locally. Picture a patch of ocean where the waves suddenly surge twice as high. Only here, the ocean is space-time itself. Then there's the dark matter factor. Hercules is already an oddball with its missing dark matter pockets, but what if those voids aren't just empty? What if they're actively repulsive? Some models propose that certain types of dark matter might interact with dark energy in unexpected ways, creating temporary push zones that accelerate expansion in fits and starts. Imagine stepping on a cosmic gas pedal only to find it sometimes sticks, except in this case, the pedal is woven into the fabric of reality, but the real curveball comes from the cluster's structure. Hercules isn't just expanding, it's doing so in rhythmic bursts, almost like it's breathing. Telescopes have caught galaxies speeding up, slowing down, then speeding up again in cycles that defy any known cosmological model. Some researchers point to the cluster's extreme density as the culprit. Perhaps the gravitational tug of war between its countless galaxies is generating shock waves that ripple outward, shoving matter apart in unpredictable surges. Others wonder if we're seeing the fingerprints of a deeper instability, a flaw in our understanding of how gravity and dark energy balance on cosmic scales. The wildest idea, Hercules might be a cosmic anomaly not because it's broken, but because it's ahead of the curve. Dark energy's influence is thought to grow over time as the universe empties out. Could this cluster be offering a preview of the far future, when acceleration runs rampant and galaxies are torn apart by the void? If so, Hercules isn't just a puzzle, it's a time capsule, showing us how the story of the universe might end long before the rest of us get there. Every new observation deepens the mystery. Some galaxies within Hercules are now moving so fast they'll eventually escape the cluster entirely, flung into the abyss like leaves in a hurricane. Others cling stubbornly to their orbits as if immune to the chaos around them. This isn't just a challenge for theorists, it's a wake-up call. If the laws of physics can bend this dramatically in one corner of the cosmos, what other surprises are lurking out there, waiting to append our cosmic playbook? Hercules doesn't just defy expectations, it dares us to imagine a universe far stranger and far more dynamic than we ever thought possible. Deep in the Hercules cluster, space itself seems to be blinking, sending out gamma-ray flashes that punch through the cosmos like a strobe light with no off switch. These aren't your typical gamma-ray bursts, those catastrophic explosions marking the death of massive stars or the collisions of neutron stars. No, these flashes are different, shorter, sharper, and far more mischievous. They arrive without warning, last mere milliseconds, then vanish only to reappear months or even years later, like a cosmic prankster taunting us from the shadows. What makes these gamma-ray enigmas so baffling isn't just their irregular rhythm, it's their sheer intensity. Each flash packs more energy than our sun will emit in its entire lifetime, all concentrated into a blink and you'll miss it pulse. Yet, unlike traditional GRBs, which light up once and fade into oblivion, these Hercules flashes repeat. Not on a schedule, not even close. Sometimes they fire off 3 times in a week, then go silent for a decade. It's as if something out there is testing the universe's mute button and failing spectacularly. So what could possibly generate such erratic yet monstrously powerful signals? One natural explanation points to magnetars, neutron stars with magnetic fields so strong they could strip the electrons from atoms light years away. When these cosmic monsters undergo starquakes, cracks in their crusts might unleash gamma-ray flares. But Hercules flashes dwarf anything magnetars are known to produce, both in energy and unpredictability. Even the most unstable magnetar shouldn't be this chaotic, this loud. Then there's the black hole angle. Some theorists suggest we might be seeing the aftermath of a black hole's messy meal, a star torn apart not in one catastrophic gulp, but in fits and starts like a predator nibbling at its prey. As stellar debris swirls into the abyss, magnetic shocks could accelerate particles to near light speed, creating gamma-ray fireworks. But again, the timing doesn't fit. Tidal disruption events flare brightly, then fade over months or years. These flashes, they're more like a Morse code from hell, brief, blistering, and utterly random. That randomness is what's driven a handful of researchers to flirt with more radical ideas. Could these be signatures of alien technology, a power source, or even a beacon, operating on timescales and energies we can't yet fathom? It's a controversial notion, but not without precedent. In the 1970s, astronomers detected the WOW signal, a radio burst so peculiar it sparked decades of speculation. The Hercules flashes feel like that signal's gamma-ray cousins, too strange to ignore, too sparse to decode. Of course, the likelier answer lies in physics we've yet to uncover. Some speculate these bursts might be tied to quantum fluctuations in spacetime itself, tiny ripples magnified by the cluster's extreme gravity into detectable eruptions. Others wonder if dark matter plays a role. Certain exotic particles, when they decay or collide, could theoretically release gamma rays in bizarre, sporadic bursts. Whatever the truth, one thing's certain: these flashes aren't just anomalies. They're challenges daring us to rethink how energy operates in the universe's most extreme environments. Every time a new one flickers to life, telescopes scramble to catch it, hoping for a clue. But so far, the Hercules Cluster keeps its secrets close, flashing its cryptic signals across the void, as if reminding us the universe's most explosive conversations often happen in whispers. In the Hercules Cluster, two stars are performing a cosmic ballet that defies all known laws of stellar physics, a pair so close they nearly touch, whirling around each other at breakneck speeds without collapsing into a cataclysmic merger. Dubbed the impossible binary, these stars orbit just a few million kilometers apart, so near that their surfaces stretch toward each other like distorted balloons, their outer atmospheres mingling in a shimmering bridge of superheated plasma. By all rights, such proximity should spell disaster. Tidal forces ought to rip them apart or trigger a violent collision within hours. Yet somehow, against every prediction, they persist, locked in a gravitational embrace that has lasted millennia. The first clue to their survival lies in their composition. Both stars are helium-rich subdwarfs, compact and incredibly dense, their cores burning with a ferocity that counters the relentless pull of gravity. Their tight orbits mean a single year for this binary lasts less than 2 Earth hours, a dizzying speed that generates centrifugal forces strong enough to keep them from spiraling inward. Think of two ice skaters spinning while clasping hands. The faster they go, the harder it becomes to pull closer without toppling over, but even that analogy falls short. The real mystery isn't just their stability, it's how they got this close in the first place. Conventional binary systems form with wide separations, gradually tightening over billions of years through processes like magnetic braking or gravitational wave emission. Yet the impossible binary's orbit is so tight it bypasses every known evolutionary pathway. One theory suggests a third star was once part of this dance, stirring chaos that flung two of them together while ejecting the third into the void. Another posits that these stars were born from the remnants of a single, massive progenitor that somehow split during its death throes like a cosmic mitosis event. But the most tantalizing idea: they might be relics of a rare blue straggler merger, a stellar Frankenstein created when two older stars collided and reignited, only to be later torn apart by the cluster's extreme gravity. The implications ripple far beyond Hercules. If stars can orbit this closely without destruction, our models of stellar evolution need serious revision. Close binaries are key to phenomena like Type Ia supernova and X-ray bursts, cosmic lighthouses used to measure the universe's expansion. If the impossible binary represents a previously overlooked class of survivors, these cosmic yardsticks might be less reliable than we thought. Even more unsettling, their existence hints at unknown stabilizing mechanisms, perhaps tied to the cluster's unique magnetic fields or dark matter distribution. But the real shock came when astronomers spotted faint, ultra-fast pulses flickering between the stars' flashes, timed precisely to their orbital period. Some speculate these could be tidal pulsations, vibrations in the stars' cores as they stretch and compress each other. Others wonder if we're seeing evidence of a shared magnetic field, a dynamo effect generated by their furious motion. Whatever the cause, one thing is clear: the impossible binary isn't just a curiosity. It's a laboratory testing the limits of physics in ways we're only beginning to understand. And as long as these stars keep dancing on the edge of annihilation, they'll keep challenging our cosmic rulebook, one perilous orbit at a time. Nestled in the turbulent heart of the Hercules Cluster, two celestial oddities shatter our understanding of cosmic chemistry. A gas cloud so saturated with metals it defies all known laws of nucleosynthesis, and a planet so dense and radiant it might as well be a cosmic jewel. These aren't just anomalies, they're cosmic alchemists forging elements and rewriting the rules of planetary formation under conditions so extreme, even the universe seems to hesitate. First, the gas cloud, officially catalogued as HCG 47, but nicknamed the Forge by researchers. Unlike typical interstellar clouds, which are mostly hydrogen and helium with trace metals, this one is laced with staggering concentrations of gold, platinum, and uranium elements so heavy they should sink into stars or planets, not float freely in space. The numbers are mind-bending. Some regions contain over 100 times the expected metal content for their volume, as if someone took a chunk of Earth's core and vaporized it across light years. How does such a metallic fog even form? One theory points to a catastrophic collision between neutron stars, those ultra-dense corpses of dead suns. When these objects spiral into each other, their mergers spray space with freshly forged heavy elements in spectacular kilonova explosions. But the forge's composition is too pristine, its metals too perfectly mixed to match the chaotic debris of such an event. Another possibility: it might be the lingering breath of a hypernova, a theoretical supernova so powerful it could seed space with metals in ways we've never observed. Or more radically, this cloud could be the remnants of a primordial star, one of the universe's first giants, whose death scattered its metallic guts far wider than any model predicts. Now shift your gaze to the second marvel, HCP-18, a planet so bizarre it gleams like a diamond in the void. Scans reveal a carbon-rich world under pressures so intense that much of its interior has crystallized into literal diamond, a gemstone the size of a planet. This isn't just speculative. Its density and thermal conductivity match what diamond would exhibit under such extreme conditions. Picture a world where mountains might be diamond shards and rivers of liquid carbon carve valleys into its glittering crust. But how does a diamond planet form? Carbon-heavy worlds usually arise around stars rich in this element, where carbon outweighs oxygen during planetary formation. Yet HCP-18 orbits a relatively ordinary star, one without the expected carbon surplus. That's led to wilder explanations. Perhaps it's the shattered core of a white dwarf, a star that once burned carbon but was stripped to its crystalline heart by a stellar collision. Or maybe it's a rogue planet born elsewhere and flung into the Hercules Cluster, carrying the secrets of its origins in its glittering depths. The real magic lies in the connection between these two oddities. Both are products of the same violent, high-pressure environments where atoms get squeezed and twisted into forms nature rarely allows. The Forge's metals and HCP-18's diamond structure are cosmic cousins, each representing extremes of elemental abundance forged in the crucible of the cluster's chaos. Together, they're a testament to the universe's ability to surprise us, transforming the raw ingredients of creation into wonders we're only beginning to comprehend. What makes these discoveries so pivotal isn't just their strangeness, it's the way they force us to revisit the cosmic periodic table. If metals can pool freely in space or planets can crystallize into giant gems, what other impossibilities are waiting to be uncovered? The Hercules Cluster doesn't just host these rarities, it flaunts them, daring us to rethink how elements are born, scattered, and reborn in the endless dance of the cosmos. And with each new observation, the message grows clearer. The universe's recipe book has pages we haven't even opened yet. Among the countless galaxies swirling through the Hercules Cluster, one stands out like a cosmic Rorschach test. A spiral system so perfectly mirrored across the cluster's central axis, it looks as though the universe itself pressed a copy-and-paste command. Dubbed the Mirror Galaxy, this celestial oddity displays near-identical star formation patterns, dust lanes, and even satellite galaxy arrangements on either side of the cluster's gravitational midline, as if nature got stuck in a symmetry loop. The odds of such perfect duplication occurring by chance are astronomically low, raising a tantalizing question. Is this a statistical miracle or a glimpse of physics playing by rules we've yet to uncover? Symmetry isn't uncommon in the cosmos. Many galaxies exhibit balanced spiral arms or evenly distributed star clusters, but the Mirror Galaxy takes this to an extreme. Its eastern and western hemispheres aren't just roughly similar, they're precision matched down to the angles of individual stellar nurseries and the curvature of their outermost hydrogen clouds. Imagine flipping a vinyl record to its B-side and finding the same grooves playing the same song, only here the record is tens of thousands of light years wide. The leading natural explanation invokes gravitational lensing, the phenomenon where massive objects bend light like a funhouse mirror. If the cluster's dark matter were distributed in a precise, symmetrical halo, it could theoretically warp the galaxy's appearance into this mirrored illusion. But there's a catch. Lensing usually distorts or multiplies images, creating arcs or duplicates offset in space. The Mirror Galaxy shows no such distortions. Its twin halves are eerily crisp, as if sculpted by an invisible hand. That's led to more radical theories, including the idea that we're witnessing a symmetry-breaking event on a galactic scale. In particle physics, symmetry breaking occurs when a system's underlying laws are symmetrical, but its observable state isn't, like a pencil balanced perfectly on its tip, only to tip one way unpredictably when disturbed. Could the Mirror Galaxy be a macroscopic version of this, where the cluster's extreme environment froze the galaxy into an unstable, symmetrical state that somehow persists? Some models suggest the galaxy might be caught in a gravitational standing wave, a rare interference pattern where tidal forces from multiple massive objects cancel out asymmetrical evolution. The wildest possibility, this could be evidence of a deeper cosmological principle that the universe has a hidden preference for symmetry under specific conditions. Certain unified field theories predict that at sufficiently high energies or densities, fundamental forces might briefly resync, imposing order on chaotic systems. If the Hercules Cluster's core acts as such a high-energy environment, it might temporarily enforce this symmetry, like a cosmic mold shaping the galaxy into its own reflection. Of course, not all researchers are convinced. Skeptics argue the Mirror Galaxy might simply be two nearly identical galaxies aligned along our line of sight, a cosmic coincidence amplified by the cluster's density. Yet even this explanation feels unsatisfying, as the galaxies would need to be not just similar in size and shape, but in identical stages of evolution with matching star formation histories and interstellar chemistry. What makes this phenomenon so compelling isn't just the mystery, it's the way it forces us to confront the limits of our cosmic intuition. Symmetry is a cornerstone of physics, from the equations of general relativity to the structure of atoms. But the Mirror Galaxy asks, how far does that symmetry extend? And what happens when the universe, against all odds, decides to hold up a mirror to itself? Every observation deepens the enigma, proving once again that the Hercules Cluster isn't just a collection of galaxies, it's a hall of mirrors, reflecting back questions we're only beginning to frame. There's a storm raging through the Hercules Cluster, one you'd never see with ordinary telescopes. Waves of dark matter, colossal in scale and staggering in power, sweep through the cluster's galaxies like a tsunami through a field of ships. These aren't gentle ripples, they're towering, coherent structures moving with a unity that defies everything we thought we knew about dark matter's elusive nature. According to the standard playbook, dark matter should be the universe's ultimate loner, particles that barely interact with each other, let alone organize into synchronized swells. Yet here in Hercules, it's doing both, and the implications are rewriting astrophysics in real time. Picture this, a single dark matter wave stretching hundreds of thousands of light years, its crests and troughs dictating the motion of entire galaxies caught in its path. Astronomers first noticed the phenomenon when they mapped the cluster's gravitational distortions, expecting the usual chaotic tug-of-war between visible and dark matter. Instead, they found eerie patterns, galaxies drifting not randomly but in unison as if riding some invisible current. The only explanation, vast, coherent waves of dark matter pulsing through the cluster with the precision of a metronome. This is where the mystery deepens. Dark matter, by definition, shouldn't form waves. Its particles are thought to be collisionless, meaning they pass through each other like ghosts, their only interaction being gravity's feeble pull. But these Hercules waves suggest something far stranger. Either dark matter can interact in ways we've never detected, or there's an entirely new force at work, one that orchestrates dark matter into structures as disciplined as marching bands. One radical theory posits that dark matter might have a hidden charge, akin to electromagnetism but operating on scales we've never probed. In this scenario, certain dark matter particles could repel or attract each other subtly, allowing them to clump into waves without fully colliding. It's like oil droplets in water, separate, yet moving as one when shaken. Another idea dives into quantum territory, suggesting dark matter waves might be macroscopic versions of quantum coherence, where particles sync up over vast distances, their states entangled across light years. But the most tantalizing clue lies in the waves' timing. They don't just roll through Hercules at random. Their spacing and speed match the cluster's gravitational echoes, ripples left by ancient collisions between galaxies. That's led some researchers to wonder if dark matter isn't just reacting to these events, but remembering them. Its waves acting like cosmic seismographs tracing violence from billions of years ago. If true, dark matter isn't just a passive scaffold for the universe, it's an active participant carrying echoes of the past in its invisible tides. The implications stretch far beyond Hercules. If dark matter can organize into waves, it might explain other cosmic anomalies, like why some galaxies rotate faster than expected, or why certain clusters seem overstructured compared to simulations. It could even hint at a deeper connection between dark matter and dark energy, the two great unknowns of modern cosmology. Are these waves a symptom of some larger, unseen interaction between them? Every new observation adds another layer to the puzzle. Recent studies have even detected faint, ultra-low frequency vibrations in the cluster, humming at frequencies that align suspiciously with the dark matter wave's motion. Coincidence unlikely. The universe rarely does anything without reason. What we're witnessing in Hercules might be the first flickers of a dark matter symphony, one that's been playing since the dawn of time, waiting for us to finally listen. And if these waves are real, they're not just rewriting the rules, they're proving the cosmos still holds movements we've yet to even name. Among the countless mysteries of the Hercules cluster, none lingers quite like its ghostly infrared glow, a persistent, all-encompassing warmth that blankets the region, defying every known heat source in the cosmos. Picture holding your hands near a fireplace long after the flames have died, only to feel the same relentless heat radiating from empty space. That's the enigma astronomers face here. The entire cluster hums with infrared light, the kind usually emitted by dust clouds warmed by stars or the friction of colliding gas. But when they tally up every star, every nebula, every speck of interstellar debris, the math falls catastrophically short. There's simply not enough visible matter to account for this much warmth. So what's cooking in Hercules? One leading suspect is a hidden population of rogue planets, not the solitary wanderers we've spotted elsewhere, but billions of them, drifting untethered between galaxies like cosmic vagabonds. These dark, frigid worlds, having been flung from their star systems long ago, would be too faint to see directly, yet collectively their residual heat, left over from formation or stirred by tidal forces, might explain the glow. It's a tantalizing idea, but the numbers strain credibility. To match the infrared signal, Hercules would need more rogue planets than all the visible stars in the cluster combined, a density that challenges our models of planetary formation and ejection. Then there's the dark matter angle, because in Hercules, it's always dark matter. Certain theoretical particles, like weakly interacting massive particles or WIMP, could theoretically collide and annihilate, releasing energy as heat. If dark matter is denser here than we've measured, these phantom collisions might be radiating infrared energy like an invisible furnace. The catch: even our most generous estimates of dark matter interactions can't fully explain the glow's intensity or its eerie uniformity. It's too smooth, too evenly distributed, as if the cluster itself is breathing out warmth in a steady, cosmic sigh. Perhaps the most radical explanation lies in the fabric of space itself. Quantum field theory suggests that a vacuum isn't truly empty. It fizzes with virtual particles that flicker in and out of existence. Under extreme gravitational stress, like that in Hercules' crowded core, these particles might release detectable energy as they form and annihilate. It's a stretch, but not impossible. Alternatively, the glow could be the imprint of a long-faded cataclysm, a burst of star formation so violent it heated the cluster's gas to lingering warmth, like a stovetop cooling hours after the burners turned off. But here's the twist: the infrared signal isn't static. Subtle fluctuations ripple through it, patches where the glow brightens or dims over decades, far too quickly for any known astrophysical process. That's led to whispers of something even stranger: energy leakage from extra dimensions. In string theory, our universe might be a three-dimensional brain floating in a higher dimensional space. If Hercules sits near a brain's fold or wrinkle, energy from adjacent dimensions could be seeping in, manifesting as this unexplained heat. It sounds like science fiction, but when the alternatives run dry, even the wildest ideas deserve a hearing. The implications ripple far beyond Hercules. If this glow stems from new physics, whether particle annihilations, quantum vacuum effects, or dimensional bleed, it could reshape our understanding of energy itself. Every unsolved infrared photon is a clue, a breadcrumb leading to forces or phenomena we've yet to name. And as telescopes grow more sensitive, the cluster's persistent warmth refuses to fade into the background. It lingers, undeniable and enigmatic, like the universe's way of reminding us some mysteries won't be solved with bigger lenses or better equations. They'll demand we rethink the very nature of reality. The missing dark matter in the Hercules cluster isn't just a local oddity, it's a seismic crack in the foundation of modern cosmology. For decades, dark matter has been the invisible glue holding our models of the universe together, explaining why galaxies spin faster than visible matter alone should allow, and how colossal structures like the Hercules cluster formed in the first place. But here, where vast swaths of this enigmatic substance have seemingly vanished without a trace, the implications ripple far beyond a single cluster. They force us to confront the unnerving possibility that our cosmic rulebook might be missing entire chapters. Take modified gravity theories like modified Newtonian dynamics, which propose that gravity behaves differently at galactic scales than Einstein's equations predict. In a universe without dark matter, would elegantly explain why outer stars in galaxies rotate at speeds that defy classical physics. But Hercules throws even that idea into chaos. While works neatly for individual galaxies, it stumbles when applied to colossal structures like clusters, where the missing dark matter's gravitational pull should still dominate. Hercules' ghostly voids, where galaxies move too fast for visible matter yet too slow for expected dark matter densities, defy both models, as if the universe is taunting us with a third option we haven't considered. Then there's the multiverse angle. If parallel universes exist, could Hercules be a cosmic leak, a region where mass from another reality bleeds into ours or worse, drains away? String theory allows for brains' higher dimensional membranes to interact gravitationally, potentially siphoning dark matter into other dimensions. Imagine a bathtub with an unseen crack. Water vanishes, but you'd only notice the dropping waterline. If dark matter is slipping through such a crack in space-time, Hercules might be the drain, its missing mass not gone but displaced into a reality we'll never see. But the boldest rethink comes from quantum gravity. Some theorists suggest dark matter's absence might signal its transformation into something else entirely, a phase transition where familiar, cold, dark matter particles decay into lighter, faster forms that evade detection. In Hercules' extreme environment, where galaxies collide and space-time warps unpredictably, such a shift could be triggered like ice melting into water under pressure. If true, dark matter isn't just a static scaffold but a dynamic substance, evolving in ways we've never witnessed, the stakes couldn't be higher. If dark matter's behavior in Hercules isn't a fluke but a clue, our cosmic census, the very balance sheet of the universe's mass and energy, might be catastrophically wrong. Supernova distances, galaxy rotation curves, even the fate of the cosmos in the face of dark energy's expansion could hinge on this puzzle. Hercules isn't just hiding dark matter, it's daring us to imagine a universe where the invisible hand guiding everything we see isn't what we thought at all. And until we solve it, every assumption about the cosmos hangs in the balance. Among the Hercules Cluster's countless enigmas, few burn as provocatively as Hercules Prime, the ancient star whose chemistry reads like a cosmic crime scene. This celestial elder, nearly as old as the universe itself, shouldn't glitter with heavy metals like gold and uranium. These elements are the products of stellar alchemy, forged in the violent deaths of massive stars or the collisions of neutron stars, events that take generations to unfold. Yet here they are, embedded in a star that predates the very processes supposed to create them. It's like finding a medieval knight buried with a smartphone. The timeline simply doesn't compute. So how did this stellar relic get so improbably enriched? The answers might rewrite not just stellar evolution but the origin of everything. Let's rewind to the universe's first minutes. In the primordial soup of the Big Bang, only the lightest elements, hydrogen, helium, and trace lithium, could form. Everything heavier required stellar furnaces or cataclysmic explosions yet to come. Hercules Prime's existence suggests an alternative. What if the early universe hosted unknown, ultra-powerful events that peppered space with heavy elements far sooner than models predict? One radical idea points to population Roman 3, stars hypothetical first-generation giants hundreds of times more massive than our Sun. These behemoths would have lived fast and died hard, their supernova so energetic they could have seeded entire galaxies with metals in a single blast. Hercules Prime might be a surviving witness to that era, its atmosphere laced with the ashes of stars that no longer exist. But there's a catch. Even population Roman 3 supernova struggle to explain the star's eerily precise mix of elements. The ratios of europium to gold or platinum to uranium don't match any known explosive nucleosynthesis pathway. That's led some theorists down a wilder path: neutron-star mergers. When these ultra-dense corpses collide, they're known to spray space with gold and platinum in staggering amounts. But Hercules Prime's age implies such a merger would have had to occur absurdly early, within the universe's first few 100 million years, a time when neutron stars were thought to be vanishingly rare. If true, it would mean the cosmos got busy building complexity far quicker than we imagined, like a child assembling a supercomputer from toy blocks. Then there's the elephant in the room. Could Hercules Prime's impossible metals hint at something artificial? Before dismissing the idea, consider the numbers. A Kardashev-type Roman 2 civilization, one capable of harnessing a star's total energy, might transmute elements on industrial scales, enriching nearby stars with engineered byproducts. The star's odd isotopic ratios, particularly its excess of certain radioactive elements with no natural production pathway, have even sparked highly speculative discussions about nuclear waste signatures. Of course, extraordinary claims demand extraordinary evidence, and no one's suggesting we've found cosmic smelting debris. But the very fact that such whispers enter scientific discourse underscores how profoundly Hercules Prime challenges our frameworks. The deepest lesson here isn't just about one star, it's about cosmic timelines. Hercules Prime forces us to confront the possibility that the early universe was a far more dynamic and messy place than our tidy models suggest. Perhaps the first stars didn't form in isolation, but in frenzied clusters where collisions and mergers spat out metals at breakneck speed. Or maybe dark matter played a role, its interactions sparking unnatural fusion in primordial gas clouds. Whatever the truth, this ancient luminary is more than a curiosity, it's a time capsule. Its light carrying whispers from an epoch when the rules themselves were still being written. And those whispers grow louder with every new telescope trained its way, each observation a chance to decode the universe's earliest secrets. The universe is expanding, that much we know. But in the Hercules Cluster, something's gone off script. While the cosmos at large grows steadily, pushed apart by dark energy's gentle nudge, Hercules is practically sprinting into the void, its galaxies hurtling away from each other at speeds that make astronomers triple-check their calculators. This isn't just a slight discrepancy, it's a full-blown cosmic mutiny, as if the cluster decided to rewrite the rules of cosmic expansion in real time. And the closer scientists look, the stranger it gets. Dark energy, the mysterious force driving the universe's acceleration, should act uniformly like an invisible tide lifting all boats. But in Hercules, the effect is uneven, almost capricious. Some galaxies race outward as if propelled by rockets, while others inch along at the expected pace. It's as if dark energy here has dials cranked to different settings in different corners of the cluster. One theory suggests the cluster might be sitting atop a dark energy hotspot, a rare concentration of this enigmatic force amplifying its effects locally. Picture a patch of ocean where the waves suddenly surge twice as high. Only here, the ocean is space-time itself. Then there's the dark matter factor. Hercules is already an oddball with its missing dark matter pockets, but what if those voids aren't just empty? What if they're actively repulsive? Some models propose that certain types of dark matter might interact with dark energy in unexpected ways, creating temporary push zones that accelerate expansion in fits and starts. Imagine stepping on a cosmic gas pedal only to find it sometimes sticks, except in this case, the pedal is woven into the fabric of reality, but the real curveball comes from the cluster's structure. Hercules isn't just expanding, it's doing so in rhythmic bursts, almost like it's breathing. Telescopes have caught galaxies speeding up, slowing down, then speeding up again in cycles that defy any known cosmological model. Some researchers point to the cluster's extreme density as the culprit. Perhaps the gravitational tug of war between its countless galaxies is generating shock waves that ripple outward, shoving matter apart in unpredictable surges. Others wonder if we're seeing the fingerprints of a deeper instability, a flaw in our understanding of how gravity and dark energy balance on cosmic scales. The wildest idea, Hercules might be a cosmic anomaly not because it's broken, but because it's ahead of the curve. Dark energy's influence is thought to grow over time as the universe empties out. Could this cluster be offering a preview of the far future, when acceleration runs rampant and galaxies are torn apart by the void? If so, Hercules isn't just a puzzle, it's a time capsule, showing us how the story of the universe might end long before the rest of us get there. Every new observation deepens the mystery. Some galaxies within Hercules are now moving so fast they'll eventually escape the cluster entirely, flung into the abyss like leaves in a hurricane. Others cling stubbornly to their orbits as if immune to the chaos around them. This isn't just a challenge for theorists, it's a wake-up call. If the laws of physics can bend this dramatically in one corner of the cosmos, what other surprises are lurking out there, waiting to append our cosmic playbook? Hercules doesn't just defy expectations, it dares us to imagine a universe far stranger and far more dynamic than we ever thought possible. From vanishing galaxies to rogue planets humming with metallic songs, the Hercules Cluster serves up cosmic mysteries like no other corner of the universe. Each of these 25 phenomena isn't just an oddity, it's a crack in the foundation of what we thought we knew. The missing dark matter defies gravity's rules. The synchronized quasars laugh at the limits of quantum entanglement. The ghostly infrared glow whispers of invisible forces cooking the cosmos in ways we can't yet measure. And that's just the beginning. The floating galaxy drifting against the tide, the phantom repeater broadcasting from nowhere, the diamond planet gleaming in the void, these aren't just puzzles. They're proof that the universe refuses to be crammed into the neat boxes of our textbooks. What makes the Hercules Cluster so extraordinary isn't just the sheer number of anomalies, it's how they intertwine. The same place where stars explode in eerie unison also hosts black holes that warp time unpredictably. The region where dark matter waves sweep through like cosmic tides is also home to a nebula laced with impossible chemistry. It's as if the cluster is a grand experiment, testing the limits of physics from every angle at once, and we're only now catching glimpses of the results. For astronomers, these mysteries aren't frustrations, they're invitations. Every unanswered question is a chance to rewrite the cosmic rulebook, to peek behind the curtain of reality and ask, what else is possible? The Hercules Cluster doesn't just challenge our models, it sparks our imagination, pushing us to consider forces we've never detected, dimensions we've never seen, and laws we've yet to dream up. So here's the real question: which of these enigmas grabs you? Is it the ancient star Hercules Prime, flaunting metals it shouldn't possess, or the phantom repeater, pulsing like a beacon with no sender? Maybe it's the Mirror Galaxy, a Rorschach test written in starlight. Drop your thoughts in the comments below. We're all detectives in this cosmic mystery together. And if you're hungry for more deep dives into the universe's strangest corners, hit subscribe. The cosmos has plenty more secrets to share, and we're just getting started.